So hello again. Tonight we're going to talk about oceans. Sounds simple and straightforward. This is a member requested presentation. Thank you for that, Manuela. Um, but I've extended it beyond just the Earth's oceans and all about them to bodies of water that might be on other planets and moons and asteroids and comets elsewhere in the solar system, and spectroscopic detection of large amounts of water on exoplanets as detected by like the James Webb Space Telescope. So we'll get into the minutiae of oceans. Ocean, everybody knows what an ocean is, but I cover a lot more detail than that. So at the end of the presentation, there's a bunch of links for the deeper divers into the ocean, the rabbit hole followers. And as I said, we'll also cover the potential of oceans on planets and moons in our solar system, and the potential for oceans on exoplanets and their moons around the billions of other stars in our galaxy. And then you can extrapolate that to billions of other galaxies, and you realize that we've got a mediocre amount of water on this planet, but there's a lot more water in the universe. So the true oceans, there's actually a definition for what an ocean is, and it's a large body of water that's not land encompassed or landlocked, and it's got a high salinity. So oceans. But then again, the oceans at the North Pole and the South Pole, because the water is so cold, the salt makes it descend, and so the water at the top is less saline, less salty than the outer ocean in like the Pacific and the Atlantic and the Indian. So people will get confused or use the same term, oceans and seas. Seas are not the same as oceans. Seas are more encompassed by land. They're not landlocked. They're just partitioned areas. So as you can see from this globe, there are small areas near shore that are seas that are not big enough and open enough to be classified as oceans, or they're near a shoreline and therefore they get claimed to be a sea. So we have our 5 oceans. We also have some large noteworthy seas like the Mediterranean, the North Sea, the Labrador Sea, the Beaufort Sea, the Red Sea, the Philippine Sea, South China Sea, Arabian Sea, and Caribbean Sea. So these are seas, but they're all just continue. I mean, there's no dividing line. Unlike the Amazon, there's no dividing line for the sea versus the ocean that's immediately adjacent to it. And then we take it to the next level, and you have gulfs and bays. So when you get closer to shore, or you get more of an encompassment, but not completely, you have areas of water that are a little less saline, and those are bays. So you have, and gulfs. So you have the Gulf of California, that's like between the Baja Peninsula and Mexico. You have a insertion area going up deep. That's the Gulf of California. Oh, there's a typo. There's 2 typos on that slide. Wow. I was rushing through this afternoon. There's the Gulf of Alaska, the Gulf of Mexico, obviously, Hudson Bay, the Bay of Biscay, having nothing to do with Biscayne Bay, the Persian Gulf, the Bay of Bengal, and the Gulf of Thailand. This is not an exhaustive list, but if you follow the links at the end of the presentation, there is a Wikipedia page that has an exhaustive list and breaks it down by continents. And the next step down is lakes. Lakes are not seas or oceans, but there are a couple of lakes that think they're seas. A sea should have some access to an ocean body. So, everybody knows the Great Lakes, but there's a little bit of channel that you can follow out the Great Lakes to get to Hudson Bay and out to the Atlantic. But it's close enough to being not flow locked and tight enough by surrounding land that It's lakes, big lakes, Great Lakes. But there are other lakes on other continents, like Lake Baikal and Lake Victoria and Lake Malawi. Lake Malawi and Victoria are in Africa. But there are 3 lakes that are landlocked. They don't have much in the way of flow from the oceans, except during, if the glaciers ever melt and the water comes into California from the Pacific Ocean, then the Salton Sea will get more water. The Aral and Caspian Seas, those are inland seas in Russia. But because they're so low, they're somewhat salty, so they think of themselves as seas. And everybody knows that rivers are not lakes, seas, or oceans, but they typically have access to seas or oceans. The mighty Mississippi, the Amazon River. There's a funny thing that occurs on the eastern side of the Amazon River, where it exits into the southern Atlantic Ocean, where there's, which is the other river? Indiro?
Solomons and Amazon. Negro and Solomons meet up and it becomes the Amazon River.
Yeah.
And then when it comes out in an estuary, and we call it the Pororoca. I don't know how.
Yes,
that
estuary is very bizarre because the sediment levels and the temperature levels are 2 distinctly different values for the main Amazon and that other lake, the other river that flows into it. And it creates this really weird, that side's brown, this side's dark blue. And it just they don't mix well. It just stays that way.
No, it takes forever to mix. And I actually swam on that area, and like the Negro River is colder, and the Solomon River, the one that is yellow, like a clay kind of thing, it's a little bit warmer, and it is amazing. And the Negro River is a little bit slimy because there is a lot of diluted plant matter, but both of them are amazing.
So this is where I was looking for that image that we found moments ago. There are a few deep spots, deep ocean trenches in the oceans on the Earth. But if you look at all the depths that we've surveyed on the Earth, the average ocean depth is only 2.3 miles. So very thin compared to the 8,000-mile diameter of the Earth. The deepest ocean trench is the Challenger Deep in the Pacific, and it's only 6.8 miles deep, or about a little under 11 kilometers. If you look at the amount of surface area that is occupied by water versus land masses, that's continents and islands and those sorts of things, the amount of water that covers the surface is a little more than 71%, but the percentage of salty water on Earth in oceans, seas, and bays is 96.54% of that 71%. So that big ball, the big blue ball we saw, that's the salty stuff. Can't drink that, can't use it for industrial processes. Then there's currents. The water doesn't just sit there, it's moving, and it's moving at different levels, and they can actually be moving different directions at different levels. This map is a little bit weird in that it's got a combination of both the low level and the high level kind of on the same thing, and they use a different color to tell you the warm water movement versus the colder water movement. And you can see in the Atlantic, the northern equatorial current comes up from Africa to the Caribbean, and then it gets warmed up. And as it gets warmed up, that's the Gulf Stream, and the Gulf Stream gets cooled down by the Labrador Stream, and then that goes across the Atlantic Ocean and becomes the North Atlantic Drift. Now, you notice that it's black and not blue. So the Gulf Stream actually heats up what would be cooler water from the Labrador, so that like Spain and the UK, Ireland, etc., are all warmer during the wintertime than they would otherwise be. Thank you, Gulf Stream. So when people talk about if that warm water gets up to Greenland and it causes enough of the glaciers to melt and release fresh water into the North Atlantic, will that remove the other currents in the area, the Labrador and East Greenland, to the point where it will shut off the Gulf Stream? And Sabina Hassenfelder says, no, that'll never happen. Okay, I'll just leave it at that. She has a lot of physics behind her name. I don't know how much ocean current knowledge she has behind her name, but as Don says, everything is physics. Don Franklin at Fermilabs. So anyway, there's lots of currents, and they're very gigantic. Some of them, the lower ones, are actually not called currents; they're called gyres, because they are below a certain level, and they move with a constant temperature flow and distribute ocean currents. So here's an infrared picture of the Gulf Stream, and you can see how the land is blue, so that's the colder land, and you can see all the heat coming off the African coast and then getting warmed up in the Gulf Stream and then going north and heading out. The Labrador current comes in here, that's the green, that's the cooler, and then the warm stuff kind of drizzles out, but this tentacle of warmth is actually making it up to Greenland now. This is an older picture. So potable water, the kind we can drink, the kind that we can use in industrial processes, fresh water. 96.54% of the Earth's water is salt water, can't drink it. 1.74% of that is locked up in ice, glaciers, and snow. You can melt it and then drink it, but it's not readily accessible for, drinking water supply for cities. And there's a lot of water that people talk about as being subsurface water. This is water below which we have yet to drill wells, because thousands of feet down, the rock temperature and the pressure is too high, and it would literally crush the pipe in the well. But we know there's water down there. But the amount of water compared to how much there is salt water is less than 2%. So we'd have to start getting really dry before we would make the effort to drill down that far. And there's water in clouds. How much water? The water vapor is very thin, so 0.001% of the total water is in clouds. Although you can put out fog collection nets along shorelines, and as the fog rolls in and gets bunched up by mountain ranges, you can collect the water out of the atmosphere for drinking purposes. They do this in Western Africa. And then people talk about water chemically locked up in geologic features like rock or lava. And that turns out to be even less than there are in clouds. That's 0.0001%. I got to trust the USGS on these numbers. This is edited from a graphic on the U.S. Geological Survey website. It shows all water and ice drained from Earth and its atmosphere into blue spheres. It shows how little fresh liquid water of all ice and water on Earth and its atmosphere is accessible and usable for drinking, cooking, showering, and bathing, flushing toilets, cleaning dishes, livestock, agriculture, and industrial processes. Water can be recycled. There's a phrase that the astronauts aboard the ISS use: yesterday's coffee is today's coffee. So the water that made up yesterday's coffee that got extruded out as urine, and when your body gets hot, humidity, they recycle all of that, run it through the appropriate filters, and that adds to the water supply for tomorrow. But that doesn't completely replace all the water. Some of the water actually escapes out in the crapsicles, the debris that comes out of the toilets aboard the ISS. That's also inclusive of water, and that's water that has to be replaced. So every time they go up there with a cargo resupply or a CRS, they have to bring, usually it's a giant plastic bag of water, because a metal tank would be too heavy and you're not going to pressurize the water all that high. So where did all the water on the Earth come from? Simple answer is, we have some people that have made postulations or guesses that haven't yet been confirmed through observations. So the first guess is, when the solar system was forming during the accretion disk collapsing into a planet, there was a lot of water that made it to the interior of the Earth. And as the materials settled towards the core, the heavier stuff, the lighter stuff came to the surface. And so that's where a lot of the water came from. Next up is comets and asteroids that impacted the Earth. We know they have water. They brought water. But how much water? So we have no definitively provable facts as to where the Earth's water came from, but we keep looking. The latest is the OSIRIS-REx asteroid Bennu sample. They're doing analysis to determine the water that was part of Bennu, is that related to the water that's part of the Earth? The Earth's dominant water is has a very small amount of heavy water in it, deuterium. But we're finding that stuff that comes from off the Earth has a higher concentration of deuterium in it. So we have no way of saying, yep, that's just like our water, because it's just H2O. But if you look at the H atom, you can add a neutron in there and get deuterium. And therefore, if we see that the dominant water on the Earth is not deuterium, but the dominant water we see coming in from comets and asteroids has deuterium in it, then either the deuterium degraded to become our light water, or our light water came from something else, like maybe the accretion disk. So keep looking. We'll figure it out. So water elsewhere in the solar system. The more we look at Mars, the more water we find on Mars, subsurface, in ice, at the poles. So what we once thought was a rather dry Mars is now becoming a wetter Mars. And the atmospheres of Jupiter, Saturn, Uranus, and Neptune have a very low percentage of their atmosphere that is water. But they're so huge that even a low percentage in their atmosphere is a large volume of water. But we're not going to get it out anytime soon. And Pluto, as we found out, it's a dwarf planet. It's in the Kuiper Belt, but it apparently has subsurface water that during the season change of Pluto, the water comes up out of the ground, freezes on the surface, and then creates a compressed layer as they go through another winter season. So we're finding water. So the Earth's moon, which we one time thought was dry, and then we realized, what about at the South Pole in the shady areas? And we found, yeah, there's water ice in there. And the things that we call maria, or seas on the moon, those are just large, flat, volcanic covered areas. They're not actually oceans. But we've recently discovered that two of Jupiter's moons, Ganymede and Europa, have large bodies of subsurface water with thick layers of ice on top of them. So as soon as we send a probe to one of these two places, and we can drill down through about 3 to 5 miles worth of ice, we may find there's a salty ocean down there. More to look for. And it turns out Enceladus also has a subsurface ocean. That's a moon of Saturn. If you just look at the potential subsurface ocean capacity of Ganymede or Europa or Enceladus, the subsurface ocean volume of any of these three moons might exceed the total quantity of water on Earth. And then there are the minor planets, asteroids, comets, planetesimals. We certainly know that that Ceres, the minor planet Ceres, has salt deposits on the surface of it, and the salt deposits are usually from some kind of liquid chemistry that gets evaporated off into space, and you're left with the salt deposits. So we don't know where they came from exactly, but could have been water on the surface of Ceres that dried up. So water beyond our solar system. We know from spectroscopic analysis that there's water in the ionized gases of nebular clouds. And remember, even a small percentage over an area that's, 10 light years across is a huge volume of water vapor. And we've also found through spectroscopic analysis that the atmospheres of some exoplanets do show indications of water. And the exoplanet needs to be in what is known as the Goldilocks zone of its parent star in order for the water to be liquid. So it's hot enough to be liquid, not so hot that it's gaseous, and not so cold that it's glaciers or ice. It's liquid. And that's just a tiny portion of the galaxy we've investigated so far. Now, everywhere on Earth that we see water, we tend to find life in various forms, be it, plankton to small amoebas to living organisms that are larger, worms, etc., all the way up to shrimps and fish and whales, and they're all in water. So we shouldn't think it's anything different as we go out into the galaxy or out into the universe, that if there's large bodies of water, there's a high probability of some form of life. So in conclusion, we have 5 primary saltwater oceans. The amount of water we have on Earth is comparatively small compared to the total mass of the Earth. So we need to properly protect it, care for it, recycle it. We don't want to run out of it. We don't want to come in short supply wherever it is on the Earth, because then we'd have to do fog reclamation or desalinization or drilling those extremely deep wells, which who wants to spend the billions on that? And as I said, we find saltwater spectroscopically elsewhere in our galaxy and in the universe. So the possibility for life is out there. We just have to go find it. And of course, some links. So Manuela, any other questions about oceans that I didn't get to?
No, not really. That's just was interesting to see how the water came to be on Earth. That, so
we have postulations. We don't have any confirmed facts yet.
That's it. I'm glad you can confirm, because I thought my research was a little faulty. I thought, but
it's very much akin to how did the moon form? When did the moon form?
Yeah.
The more we look at it, the more like the last thing we thought of was pretty good, but there seems to be some when did it happen? How long did it take to form? Kind of questions that are just postulations, because none of us were there.
Yeah.
So what we can do is look at the geology of the rocks, and in the case of water, all we can do is look at the subatomic structure of the water molecules.
Yeah, so we kind of figure out that before we thought that what brought water to Earth was the beginning of those hypotheses is that the water came from comets during the changing of the position of the Jupiter and Saturn, and we have a very chaotic. So during the late bombardment, we thought the comets brought the water to Earth. Then we start going through samples, looking at the isotopic composition. That's what Monroe just mentioned, is looking for elements and how heavy they are, how much nitrogen they are. It's not just the water. We can look at other elements, but mostly water because we are interested in water. And we figure out that it's not coming from comets. Some very small proportion could be comets. So then they start looking at bodies in the Kuiper belt, and the bodies in the Kuiper belt has a similar composition that is like close to comets. So then they go like, not from the Kuiper belt, not from the Oort cloud. So let's check the asteroid belt. So as our telescope's starting to get better and better, we noticed there was some comets in the asteroid belt, something that we didn't know. And the definition of asteroid and comet started to become a little bit harder because they have similar compositions in the general formation of the planetary nebula. They end up having the same chemistry. The difference is that when you're coming closer to the sun, you start evaporating material, you name it comet. But if you're far away, or if you evaporate all your gases, you're an asteroid. So the composition is very similar. Now, with the latest tests that we are doing, like Bennu and near Earth orbit comets, and some of the stuff that we find in the asteroid belt, we started to looking for that we are kind of zooming to get some of the water came from carbonaceous chondrites. That's what we call it. Some of the very dark asteroids that we have in the asteroid belt, they were just lodged out of their orbits because of the changing and the dancing of Jupiter and Saturn during the formation of the solar system. So you have the late bombardment, and those carbonaceous chondrites brought some of the water. And now to complete the hypothesis of the formation of the water in the planet, some of the water was what Monroe mentioned, is that the spilling out of the natural water of planet Earth end up on the surface because of the raining down of the heavy stuff and the floating up of the lighter stuff. So you have the vapor of water that was mixed to the rock going into the surface too. So there is a mix of things. And then you have to remember that after the body that collided with Earth, we call it Theia, that is about the size of Mars, that as it collided with Earth, formed the moon. We lost a lot of the water by that very energetic impact. So there was a huge mass that we lost part of the mass of the Earth. That body lost part of its mass, and whatever is left over from the Earth and the moon. And during that very energetic process, we lost a lot of that first spilling out of water, the natural water that was in the material that formed Earth. And so that's the two hypotheses. And by the way, there is a lot of water locked into those areas where you have subduction zones under the oceans, because the water of the ocean is going together with the material of the Earth going under. So we have a lot of vapor water locked into the rocks in the mantle. So that water is also coming up slowly. But the average and whatever we are zooming in, the most hypotheses that are most established are that we have one, the natural material of the Earth had some water, and also the carbonaceous chondrites, they are located in the asteroid belt and near Earth orbit, were the objects that might have brought the water on planet Earth. So that was a very nice presentation, Monroe. I love that thing.
Yeah, it's great.
So what we may find out is that the water that we've seen beyond the Earth has always been in areas that are under direct bombardment by solar radiation. And that could allow it to sustain its heavy water state for billions of years, because you have the sun as a continuous source of particles.
The source to form heavy water, like deuterated water.
Yeah.
It's not from bombardment from the sun. You have some, but the proportion is very small. Mostly is the material that were in the composition of the solar nebula. The one that decays is tritium. Deuterium doesn't decay.
Right. Well,
And you mentioned a different word now. I knew it as Mariana Trench, the deep.
it's just Americanization. Challenger Deep.
Yeah. Well, I was, my time we mentioned it, Mariana Trench.
The Mariana Trench is the entire trench area, and the deepest part of it is the Challenger Deep, and that's because the bathysphere that went down there was called the Challenger.
Yeah.
Oh, okay. Because
that's why it's called
all over the
Deep.
world all over the world we call it Fossas Marianas.
Yeah, but I was the British taught us this way, and in America it was a different way to mention it.
Well, the entire trench area is still called the Marianas. It's just the deepest part of it is called Challenger Deep.
The Challenger, which is the more precise.
And I bet the Challenger Deep was a American ship.
Yes, was a ship.
But until somebody spends the billions and goes down there again, no naming rights.
It's quite a job. Yeah. Well, fascinating. It was great. Thank you.
You're welcome. Then there's some areas on Earth that has a different isotope composition because the lighter water evaporates. So some high altitude lakes, they have a little bit higher proportion of deuterated water because the lighter water evaporates easier. So we cannot look and compare some areas that are, high altitude lakes and stuff because they have different proportions in that deuterated water. And so there's some stuff that complicated thing. But what they do, they average out the isotopic composition of planet Earth, and also they average out like many bodies. So it's like the data from Bennu will not be conclusive because we will need more studies because it's the interesting thing about the asteroid belt is you can divide the asteroid belt in half. Half of the asteroid belt, you have body has less water because they're closer to the sun because the vapor line of the sun during the formation of the sun where you have the dry stuff and the rocky planets and the rocky area of the asteroid belt is this side towards to the sun. And then from this side, the half of the asteroid belt, it's frozen gases and everything and more like the composition of the stuff from the rest of the solar system. So you have to zoom in which area of the asteroid belt that water came from. So it gets a little bit complicated, but those dry surface asteroids that look like, dark potatoes, like burned potatoes that have weird, if you look at the average composition of those bodies, they are like, imagine a charcoal powder that is very wet. That's kind of how they are made of. And those bodies have lots of water. They're almost like permafrost. So lots of dust and materials and carbon, but they're mixed some layers of water. And that's how the water that came to here might have come from during the lake bombardment.
I think we'll probably get some insight when we can drill down below the subsurface ice layer of the moons of Jupiter and Saturn, because that would be, as the saying goes, pristine water.
Yeah, but I'm afraid that when you actually do that, we're going to contaminate those moons.
You're going to what?
You're going to contaminate those moons.
Oh, likely, but it's a small contamination, and Ganymede is the largest moon in the solar system.
Yeah, I think we're going to contaminate those. I think,
Well,
you know, like,
when we send a probe to deep space, we do use cobalt radiation to ionize anything that would be living on it. So there may be chemistry on there that we might not have cleaned off, but there certainly won't be anything living.
maybe because there's some, I think, bacteria that can survive some of that. They have one strain of bacteria that they try to kill on one of those, you know, packing facilities,
Mm-hmm.
and it is like they even name it something like streamers something because it was very hard to kill that damn thing.
Right,
And I'm
but they
afraid
know
that,
what that is. They know what that is, and they can readily recognize it. So if
sure,
that's the only living thing that they find on Ganymede below the surface of the ice, it's kind of
yeah.
indicative we brought it with us.
But it's
If they
hard
find,
to get prions, and prions can kill any kind of organism. Prions are very dangerous too.
yes.
I'm really afraid that when they do that, and that is like in the case of Europa, that is an easier way for you to analyze Europa. Europa has cryovolcanology,
Yes,
so
it
they
is
have
geysers of water.
geysers of water that's coming from the subsurface. If we concentrate in satellites that can capture that data, that material, you will have more lucky and less risk to contaminate. You don't have to drill, you don't have to do anything. All you have to do is be lucky enough to bring the spacecraft where the spray of the thing was. And we did
And
before, even the spacecraft was not prepared to do that. We actually did and analyze a little bit of the composition of the
yes,
cryovolcanoes.
yes,
And the spacecraft wasn't even designed to do that, and they figure
right.
out a way. Imagine if we actually do a specific spacecraft to analyze that. That would be, there we go. You don't have to, you know,
We
drill.
just need an autonomous prospector orbiter with a landing craft, and when a geyser goes off, you descend the landing craft to the surface and go over there and just pick up and analyze the fresh ice.
I
Because
don't know.
what we
I
get out
don't
in
think
space has been exposed to radiation
Europa
from Jupiter and Saturn.
Europa doesn't belong to us, Monroe.
Okay, we'll go to Ganymede. There was nothing in there about Ganymede.
Yes, but I don't think we should go to Europa.
But,
Europa doesn't belong to us.
Ganymede is the largest moon in the solar system. So if we're not
Yeah,
supposed to go to Europa, we'll go to Ganymede and go, mine.
but okay. So, how is the phrase? Like, I forgot. All those roads come. How do you say?
All these worlds are yours except Europa. Attempt no landing there.
Yes,
Uh-huh.
we should follow that advice.
The way that Roy Scheider concluded the movie was by saying, "We got a warning from the landlord."
Yeah,
So
that was very inspired. Did they study a little bit of,
yeah,
to
they had
write
access
that?
to Sagan. Yeah, they knew about it.
Okay, because
Yeah,
it was very
yeah,
interesting.
yeah. 2010.
That's,
Arthur C.
yeah,
Clarke. He kind of hung out with all those guys.
okay, yeah. Advised a lot of people.
Yeah, yeah,
That was very impressive.
yeah. How can we not do that anymore?
Yeah,
We don't
like
postulate.
even Dune, the way they wrote
Yeah.
and talk about the desert ecology and the way that water traps and stuff. Like you reading the book,
Hmm.
that guy was studying ecology, and
Yeah.
he knew what he was doing. It was impressive, writing.
So there was a little more about the geology and chemistry of Arrakis in the more recent Dune remake movie.
So,
Any more comments about tonight's presentation?
no, no more.
Okay.
Thank you so much.
I'm going to stop sharing and stop recording.
Okay, there we go.